Welcome to Outliers, Bell Curves, and the story every data point tells. I want to start today with a question, and it's one that sounds simple but is actually kind of profound. If I told you a student scored 72 on a math test, is that good? I mean, is it? You'd probably say, well, it depends. Depends on what everyone else scored, depends on how hard the test was. And that right there, that instinct, is exactly what statistics is built on. Today we're going on a journey through 5 connected ideas that all answer that same question. Where does one number actually stand in the big picture? Buckle up. Let's start with z-scores, because this is the hero of our story. Imagine 2 students, let's call them Maya and Theo. Maya takes a history test where the class average was 60 and the standard deviation was 10. She scores 80. Theo takes a biology test where the average was 75 and the standard deviation was 5. He also scores 80, same score. But who actually did better compared to their class? That's where the z-score comes in. Here's the idea in plain English. Take your score, subtract the mean, then divide by the standard deviation. That's it. Maya's z-score? 80 minus 60 divided by 10, that's a 2. Theo's 80 minus 75 divided by 5, also a 2. Okay, tie game in this case. But here's the power. If Theo had scored 85, his z-score would be a 2.5, meaning he sat 2.5 standard deviations above his class average. The z-score strips away the noise of different scales and tells you one clean thing. How far from average in standard deviation units is this value? It's like a universal translator for data. Now, before we can talk about what a z-score means, we need to talk about the shape of the data it comes from. Because shape changes everything. Picture a histogram, a bar chart of your data. Sometimes it's perfectly symmetric, like a bell. The mean, median, and mode all huddle together right in the center. That's your classic symmetric distribution. But data in the real world, it gets messy. Think about household income in the United States. Most families earn somewhere in the middle range, but then there are a handful of billionaires at the top, and their enormous incomes drag the mean way up to the right. The median, the true middle value, stays closer to what a typical family earns. That's called a right-skewed distribution. The tail stretches to the right, and the mean gets pulled along with it, landing above the median. Now flip it. Think about age at retirement. Most people retire somewhere around 65, but a few retire super early, at 35, 40, and those low values drag the mean to the left. That's left skewed. The tail goes left, and the mean dips below the median. Here's your memory trick. The skew follows the tail, and the mean chases the tail like a dog chasing a car. All right, so now we know shape matters. But here's a question. What can we actually guarantee about where data falls, regardless of shape? This is where Chebyshev's theorem walks in, and honestly, it's kind of underrated. Chebyshev said, no matter what your distribution looks like, skewed, weird, lopsided, whatever, at least 75% of your data will always fall within 2 standard deviations of the mean. Always. And at least 89% will fall within 3 standard deviations. Think of it like a minimum guarantee. It's the floor, not the ceiling. Chebyshev doesn't care if your data is shaped like a bell or a skateboard ramp. It works for any distribution. That's its superpower. Now, what if your data is shaped like a bell? Then we get to use something even more powerful, the empirical rule. And this one has a nickname, the 68-95-99.7 rule. Here's the story. In a perfect bell-shaped normal distribution, about 68% of data falls within 1 standard deviation of the mean. Go out to 2 standard deviations, now you've captured about 95%. 3 standard deviations? Almost everything. 99.7%. That's basically all of it. But, and this is critical, the empirical rule only works for bell-shaped distributions. That's the trade-off. Chebyshev gives you a guarantee everywhere, but with looser numbers. The empirical rule gives you precise, beautiful percentages, but only when the shape cooperates. 2 tools, 2 situations. Know which one to reach for. Okay, final chapter. And this one's about the outliers, the lone wolves of data. The values so extreme they make you go, wait, is that real? We have two ways to catch them. Method 1. Z-scores. If a data point has a z-score beyond +3 or below -3, it's a flag. It's sitting more than 3 standard deviations from the mean, way out in the tails. Statistically speaking, that's unusual enough to investigate. Method 2 is the IQR method, and this one doesn't even need a normal distribution. Find Q1 and Q3, the quartiles that split your data into fourths. Calculate the interquartile range, the IQR, by subtracting Q1 from Q3. Then set your fences. The lower limit is Q1 minus 1.5 times the IQR. The upper limit is Q3 plus 1.5 times the IQR. Anything outside those fences, outlier. Flag it, investigate it. It might be a data entry error. Or it might be the most interesting data point in the whole set. All right, let's land this plane with a quick recap. 5 ideas, 20 seconds, go. Z-scores tell you how many standard deviations a value sits from the mean. Distribution shape. Right-skewed means the mean is above the median, left-skewed means it's below, and symmetric means they're basically equal. Chebyshev's theorem guarantees minimum percentages within any distribution. The empirical rule gives precise 68, 95, 99.7 percentages, but only for bell curves, and outliers get caught by either the z-score method or the IQR fence method. That's the story of a single data point, and now you know exactly how to find where it stands. See you next time.